Okay, let's look at graphs of reaction rate. They like to ask these questions with graphs, and we always have to have a graph, dependent, independent. The time is always the independent variable. Time is always on the x-axis, and the concentration of the reactant or the product will be the dependent variable on the y-axis. So if we want to get the rate of reaction, okay, now you can see that this is a curve. So the moment that you've got a curve, how do you find the gradient? You find a tangent to the curve. I hope your maths is there. So if we want to find the rate of reaction versus time, you take the gradient at a specific point, okay? Any time, in any calculation that you do involving a gradient, write the gradient formula. Like it's not on your data sheet, you can write anything that looks like a gradient formula. y2 minus y1 over x2 minus x1, delta y over delta x, whatever. Write a gradient formula. So if we look at this curve here, you can see initially the speed of reaction, the rate of reaction is very high, and then the curve gets more gentle. If you have to draw a tangent here, you can see that the gradient is very, very low. The reactant has almost gone to completion. And this shape of this curve is also very easily explained by collision theory, because in order for a reaction to occur, the reactants and products must have successful collisions. So in the beginning, you've got a lot of reactants. They're at a high concentration. There's a lot of successful collisions. You're going to form products really, really, really fast. But as the products form, they leave behind less and less reactants until eventually the particles are still running around banging into each other, but it's nearly all product banging into each other. There are hardly any reactants to bang into each other and make an effective collision, so the reaction rate tapers off, and then when the curve goes flat, the reaction is complete. It can be complete because it's gone to completion, or it can be complete because there's a limiting reagent. Okay, so here goes. That's how the curve goes. Always write your gradient formula, and remember that time usually goes on the x-axis. So you can see here there are all of these tangents here. Look, this tangent's almost vertical, this tangent's less, and eventually when you get to rate 5, if you look at rate 5 as opposed to rate 1, you can see how much slower it's getting along the way. Of course, you can do something to this graph to make it a straight line, and then you have to pay attention to what's going on your axes, because obviously they like you to find the gradients of straight lines. They don't often ask you to draw tangents. So you can use concentration, you can use mass, you can use all sorts of different things on this axis, so long as it's however you're measuring the rate of reaction, and obviously time on the other axis. So this is a nice picture. I like this picture, okay? Here we've got a reaction of purple things turning into green things. So the purple things are the reactants, and the green things are at the products, okay? So if you have a look here, in the beginning there's a very high concentration of purple things, and then as time goes on, the purple things are turning into the green things. So if we count the number of purple things in each jar, can you see it's getting less and less and less until there's hardly any? And this is represented on this graph like this, until finally there's no purple things left. There's literally no more molecules of reactants left. At the same time, we start with everything purple. There are absolutely no green things in here. Remember, the green things are our products. So there's no products in here. In the next jar, there's a few more, a few more, a few more, until finally it's all green. So the concentration of the products is gradually increasing with time until there's no more reactants to react, and the graph levels out and the reaction has gone to completion. Okay, so this is a very nice picture to show you how is this graph derived. So if we go from purple reactants to green products, the reactant concentration drops until there's no reactants left, and the product concentration rises until the reaction has come to completion. And I think that is the end here. Okay.